Chapter 7.1 Characteristics of Exponential Functions. An exponential function is a continuous function in the form f of x equals c to the power of x, where c is the base and x is any real value. So we have our variable in the exponent for exponential functions. Note, we can use any letter to represent the base. We use c to avoid confusion when applying transformations with the parameters a, b, h, and k. Investigate when c is greater than 1 or c is greater than 0 but less than 1. Example, sketch and label the graphs of y equals 2 to the power of x and y equals 5 to the power of x. Fill in the table of values. Y equals 2 to the power of x when x is negative 2. 2 to the power of negative 2. Our exponent laws we learned in Math 10C tell us that that equals 1 over 2 to the power of positive 2, which then equals 1 over 4. 2 to the power of 2 is 4. 2 to the power of negative 1 equals 1 over 2 to the power of positive 1, so 1/2. 2 to the power of 0, any non-zero number to the power of 0 equals 1. 2 to the power of 1 equals 2, and 2 to the power of 2 equals 4. We can plot those points on our graph. X is negative 2, y is 1/4, so somewhere down here. X is negative 1, y is 1/2, about there. X is 0, y is 1. X is 1, y is 2. X is 2, y is 4. And I could do a few more going in the positive direction. If x is 3, 2 to the power of 3 is 8. When x is 4, 2 to the power of 4 is 16. And when x is 5, 2 to the power of 5 is 32, which is not on here. I can join these points together with a curve. And it looks something like that. That is y equals 2 to the power of x. Next, let's do y equals 5 to the power of x. When x is negative 2, we have 5 to the power of negative 2, which equals 1 over 5 to the power of 2, which is 1 over 25, which is a very small number, very close to 0. Then 5 to the power of negative 1 equals 1 over 5 to the power of 1, which is 1 over 5. Bigger than 1 over 25, but still pretty close to 0. 5 to the power of 0 equals 1. 5 to the power of 1 equals 5, and 5 to the power of 2 is 25. I can plot these points. When x is negative 2, we have something really close to 0. When x is negative 1, we also have something really close to 0. When x is 0, y is 1. When x is 1, y is 5. And when x is 2, y is 25. Attach those points with a curve. And that's the graph of y equals 5 to the power of x. What is the domain and range of both graphs? For both graphs, they continue left forever and they continue going out to the right as they go up. So our domain is going to be x such that XER. Our range, we never get a negative number. We're continuing this way, but we never cross the x-axis. So for both graphs, our range is y such that y is greater than or equal to 0, YER. And this is for both graphs, y equals 2 to the power of x and y equals 5 to the power of x. What are the x-intercepts? We don't have any x-intercepts. We never touch or cross the x-axis. What are the y-intercepts? Both of these have y-intercepts at y equals to 1. Or we can write that as 0, 1. What is the equation of any asymptotes? We have a horizontal asymptote at the x-axis, which is y equals 0. The reason we have a horizontal asymptote and we never touch or cross the x-axis is because when we have a negative number in the exponent, that just means 1 over the base to the power of the positive of that exponent. So -2 gives us 2 to the power of -2, which is just 1 over 2 to the 2, which is 1 over 4. If we did exponent of -3, we would just get 1 over 2 to the power of 3, which would be 1 over 8, which is still a positive, just a smaller positive. If we did x equals -4, we'd get 1 over 2 to the power of +4, which is 1 over 16, which is still a positive, but it's going to be even smaller than 1 over 4. So we're approaching 0 as we get smaller and smaller negative numbers for x, but we're never going to actually equal 0 or a negative y value. Therefore, we get a horizontal asymptote at y equals 0. Are the graphs increasing or decreasing? Both of these graphs are increasing. How do we know they're increasing? They go up to the right. This is Editing Corey here. We have an error here in the range of y equals 2 to the power of x and y equals 5 to the power of x. I put the range is y is greater than or equal to 0. That should just be y is greater than 0. So erase the equals to, and now we just have y is greater than 0. Fill in the table values for y equals 1/2 to the power of x and y equals 1 over 5 to the power of x. Sketch and label the graphs above. Now we're filling in the table for 1/2 to the power of x. If x is -2, we have 1/2 to the power of -2. We flip the base fraction, which gives us 2 over 1 to the power of +2, which is just 4. Then 1/2 to the power of -1 would equal 2 over 1 to the power of 1, which just equals 2. One-half to the power of 0 equals 1. 1/2 to the power of 1 equals 1/2, and 1/2 to the power of 2 is 1 over 2 to the power of 2 is 4. We can graph these points. When x is -2, y equals +4. When x is -1, y equals 2. When x is 0, y is 1. When x is 1, y is 1/2. When x is 2, y is 1/4, so about there. And if I go do some more on the left, if x equals -3, I have 1/2 to the power of -3. Flip the base, I get 2 over 1 to the power of +3, which is 8. So when x is -3, y is 8. If x is -4, flip the base, I get 2 over 1 to the power of +4. 2 to the power of 4 is 16. So when x is -4, y is 16. Then I can attach those points. And that gives me y equals 1/2 to the power of x. Next one, 1 over 5 to the power of x. When x is -2, we have 1 over 5 to the power of -2. Flip the base, we get 5 over 1 to the power of +2, which equals 25. 1 over 5 to the power of -1 equals 5 over 1 to the power of 1, which is 5. 1 over 5 to the power of 0 equals 1. 1 over 5 to the power of 1 equals 1 over 5, and 1 over 5 to the power of 2 is 1 over 25. Plot those points. When x is -2, y is 25. When x is -1, y is 5. When x is 0, y is 1. When x is 1, y is 1/5, down here somewhere. When x is 2, y is 1 over 25, so really close to 0. Attach the points. And we get the graph of y equals 1 over 5 to the power of x. What characteristics are common to the first two graphs you investigated? So with the last two, the 1 over 2 to the power of x and 1 over 5 to the power of x, what in those graphs is the same as 2 to the power of x and 5 to the power of x? If we look at the domain and range, the domain and range of 1/2 to the power of x and 1/5 to the power of x, they continue going forever left and forever right. So domain is XCR, and the range is y is greater than 0. So we can say that those are the same. Domain and range are the same as our first two graphs. All of them have a y-intercept at 1. Our two new graphs also don't have x-intercepts. And we also have horizontal asymptotes at the x-axis. How are the graphs different? So how are these last two graphs different from the first two? Well, the only thing different we see is the direction. These ones are going up as they go from left to right. These two are going down as they go from left to right. So these would be decreasing, whereas the first two were increasing. Why is y equals 1 to the power of x not an exponential function? 1 to the power of, let's say, -2 equals 1 over 1 to the power of 2, which equals 1 to the power of 2, which is just 1. Another example, 1 to the power of 5 equals 1. Another example, 1 to the power of 0 equals 1. So any number in the exponent is going to give us a y value of 1. So we can say all y values for y equals 1 to the power of x are 1. So y equals 1 to the power of x is just a horizontal line at y equals 1, which is not an exponential function. Summary: for an exponential function, y equals c to the power of x, the y-intercept is 1, so it passes through the point 0, 1. We have no x-intercept. We have a horizontal asymptote at y equals 0. The domain is XER. The range is y is greater than 0. When c, the base, is greater than 1, the graph is a growth function, or is increasing. And when c is a fraction between 0 and 1, the graph is a decay function, or decreasing. Notice that we never have the base of the exponential function equaling a negative. Why is that? Well, let's take the example if we had -2. And if we did -2 to the power of 1, that equals -2. -2 to the power of 2 equals +4. -2 to the power of 3 equals -8. -2 to the power of 4 is +16. So if our base is a negative, then we're jumping back and forth between positive and negative values. So we're not going to get a graph where we can join the points together. So that's why we only have c values greater than 0 for exponential functions. Writing equations. Determine the equation of the following exponential function. Make a table using the values on the graph. So our graph, we have the point 0, 1, we have the point 1, 5, and we have the point 2, 25. Our function would be y equals c to the power of x, And to determine the equation of the function, we just need to determine the c value. The point 0, 1 would tell us that 1 equals c to the power of 0. 1, 5 tells us that 5 equals c to the power of 1. And then 2, 25 tells us that 25 equals c to the power of 2. So you can probably guess that our c value needs to be 5, since 5 equals c to the power of 1. Another way that we can see this is increasing by 1, and this is being multiplied by 5. Here we are increasing by 1 again, and to get from 5 to 25, we multiply by 5. So that tells us that the base is 5, which is our c value. So our equation is y equals 5 to the power of x. Example, write the equation of a decreasing exponential function which has a y-intercept of 1, horizontal asymptote of y equals 0, and passes through the points -1, 2 and -2, 4. We can do exactly as we did above, make a table of values. Go from lowest to highest with your x values, so -2, 4. Then -1, 2. Then we have the y-intercept, which is an x value of 0, and it says the y-intercept is at 1. Our function is y equals c to the power of x. The point -2, 4 tells us that 4 equals c to the power of -2. The point -1, 2 tells us that 2 equals c to the power of -1, and the point 0, 1 tells us that 1 equals c to the power of 0. If we look at our x values, they are increasing by 1. -2 to 1 is +1, -1 to 0 is +1, and our y values 4 to 2, we'd have to multiply by 1/2. 2 to 1, we are multiplying by 1/2. Then our base number is 1/2, which is our c value. So our equation becomes y equals 1/2 to the power of x. Applications. A bacteria culture triples every week. This is modeled by the graph below. A. What are the domain and range? So domain is our time, in this case, in weeks. Time cannot be negative, so time's going to start at 0, and then it's going to increase. We see that our graph has an arrow, so there's no stopping point. It is continuing on. Then domain would be x such that x is greater than or equal to 0, XER. The range represents the number of bacteria. The number of bacteria starts at 1. We see here the y-intercept is 1. Then the range is y such that y is greater than or equal to 1, YER. B. Write an exponential growth model that relates the number of bacteria B to time in weeks. Time in weeks T, that's our x value, and then the number of bacteria B is our y value. We have the points 0, 1, 1, 3, and 2, 9. So here in time we are increasing by 1, plus 1, plus 1. And then to go from 1 to 3, we would have to multiply by 3. 3 to 9, we would have to multiply by 3. So that tells us that our C value equals 3. Then our function is bacteria is a function of time, which equals 3 to the power of t time in weeks. Part C, how does what's happening to the population each week relate to the equation? The population is tripling each week, which means multiply by 3. Hence the C value being 3. D, how many weeks would it take for the number of bacteria to be 8 times the quantity on week 1? On week 1, we have a population of 3 bacteria from the point 1, 3. B equals 3. We want to know how long it takes for the bacteria to be 8 times the quantity on week 1. So 3 times 8 is 24. Then we can use our graphing calculators, do y1 equals 3 to the power of x and y2 equals 24. And then find the x values of the intersection points. Three to the power of x for y1 and y2 is 24. Graph that. I probably need to change my window. I need to go up at least to 24, so I'll go to 30 and graph that. There we go. Second trace, number 5. Enter, enter, enter. We get x is 2.893. Or x is approximately equal to 2.9 weeks. Part E, how many bacteria are present at the beginning of the experiment? Beginning of the experiment would be at week 0, where we have the y-intercept 0, 1. That tells us at week 0, the beginning of the experiment, there is 1 bacteria. Example, the intensity of light below the surface of a lake is reduced by 5% for every meter below the surface. When we have questions that involve percent, change that to decimals. So divide by 100 gives us 0.05. A, write an equation that models the intensity of the light at any depth. the intensity of the light at any depth, that would be the light remaining. We know that the light decreases by 5% for every meter. So the remaining amount of light at each meter would be 100% minus 5%, which is 95%, which as a decimal is 0.95. Then we would have Y, which is the amount of light remaining, is equal to 0.95, the amount of light remaining for each meter of depth, to the power of x, the number of meters of depth. B, what percent of the original intensity of the light remains 12 meters below the surface? That would be y equals 0.95 to the power of the depth, in this case, is 12. Then we calculate that. .95 to the power of 12 is 0.5403. This is the percent as a decimal, so we need to convert it to percent by multiplying by 100, which is approximately equal to 54%. Part C, determine how far below the surface the intensity of light remaining is 30%. So 30%, change that to a decimal, is 0.30. This is the light remaining, that's our y value. So now we have 0.30 equals 0.95x. To determine the x value, we use our graphing calculator, put y1 equals 0.95 to the power of x, and y2 equals 0.30, and then find the x value of the intersection point. Go to y equals, clear that, 0.95 to the power of x, and y2 is 0.3. Graph that. I can change my window. I'll try zoom fit number 6. Okay, so I need to move farther to the right, so I can change my window and change my x max to maybe 50. And I'm going to move a little bit down as well. So my y min, let's change to -2. And there I can see my intersection point nicely. So second, trace, number 5, enter, enter, enter. And it tells me that my x value is 23.44. That's actually a little bit inaccurate. You can see that it's telling me my x value for y equals 0.300497 ... Should be telling me my x value for y equals exactly 0.3. So when I do it on my Casio graphing calculator that I have, it gives me x equals 23.4723 ... So x is approximately equal to 23.5, and that was the distance below the surface, so that's measured in meters. I have noticed some issues with this graphing calculator app. It's not always as accurate as an actual graphing calculator, so I will try to point that out anytime it happens. And hopefully with your graphing calculator, you get the exact values. You should. I definitely did with my Casio. I don't have a TI with me to attempt it right now, but you should get the 23.4723 ... And that brings us to the end of Chapter 7, Lesson 1.